Good day, everyone. And once again, we're back together. All right, so I hope that you wrote well for your first paper. And of course, this time we're going to be just revising on the second paper. So I thought I just would start with chemical equilibrium. Right, so let's dive right into it. Okay, right. So they say the balanced equation below represents the reaction that reaches equilibrium in a sealed container, right? So we've got N2 plus 3H2, which will give us 2NH3, okay? And delta H rather is less than 0. Right, so they say to us to increase the yield of ammonia, adjustments are made to temperature, pressure, and concentration of the mixture. The graph below represents the results obtained. Right, so now let's have a quick look at, this graph question. So just a quick analysis on the graph, right? So if you look at this, this graph, when you look at it, is a graph that starts at equilibrium, right? And how do you know? Because all the amounts are constant at the beginning, right? So we're not starting right from the beginning where, you still have reactants, just only reactants and no products, but we already have all of them, right? And it's at equilibrium. Now, a change was made at T1. Now, what I want you to note, at T1, you've got a sharp spike on nitrogen there, right? So it must tell you that the change that was made at T1 must be a change, in this case, in the concentration of nitrogen. So it was an increase in concentration of nitrogen, right? So that's the change. So we know that T1 has to do with concentration. Okay, they said identify the changes made in the equilibrium mixture of the following at the following times. So that was a change in concentration. Okay, and then in this case at T2, please note that all of them suddenly have this sharp spike. Remember, this is a graph of concentration. So what is concentration? It's number of moles over volume. So it means, in this case, for them to change concentration for all of the amounts, it must mean that we must have tempered with the volume, right? By the way, just to note there, it means that there must have been a decrease in volume, which means an increase in pressure, right? So as a result, that was the reason why there was that change in the concentration for all of them. But nonetheless, after that, then equilibrium starts to take effect. Of course, there'll be a reaction that is favored. We'll perhaps look at that a little later on, right? So T2 was a change in pressure. So that was a change in pressure. And then at T3, obviously, they said 3 changes, so it must be that at T3, that must have been temperature. Okay, right. Okay, so that's our answer when it comes to that portion, right? They didn't ask whether it will increase or decrease, but we just needed to identify what causes the change in that regard. Okay, right. Now, let's go to the next question. Actually, I was supposed to answer that over here, but nonetheless. Okay, right. The next portion, they say to us, state Le Chatelier's principle in words. Remember, we say in a closed system, if one of the factors affecting equilibrium changes, then equilibrium will oppose the change and a new equilibrium will be established, right? Okay, of course, there are other ways of also expressing the same thing, but nonetheless, it is what it is, right? Okay, so for 6.3, they say the pressure in the reaction mixture in question 6.1 above is disturbed by increasing the volume, right, in the container. So now they're asking us, all right, how will the change above affect the yield in NH3, of NH3 rather, right, down only increase, decrease, or remain the same. Now, please, I want you to note, let's talk about this a bit. Okay, so now they are telling us that they are going to increase the volume, right? So what does an increase in volume mean in this case? It means that we are decreasing the pressure, right? Now, remember, according to Le Chatelier's principle, once you increase the volume, you favor the side. Now, when it comes to pressure or volume, you always look at where there's more moles of gas, right? So in this case, there's 1 mole plus 3. So on the left-hand side, we've got 4 moles of gas, right? And then on the right-hand side, we've got only 2 moles of gas. Please check that you only count the moles of gases. If it's not a gas, don't count it, right? So now we've got this 1 plus this 3. We've got 4 on the left. We've got 2 on the right. So an increase in the volume in this case will favor the side with the greater mole amount, okay, or volume in this case of gases, right? With a greater volume of gases, right? Because remember, the gas is trying to fill up as much of the container as possible. So when we increase the volume, we're going to favor the side with more moles of gas, right? So as a result, it means that we will favor the reverse reaction, okay? So as a result, it means that our yield will decrease, right? So we can answer that question and say, well, it means that our yield, first of all, will decrease, okay? And they would like for us to explain that, okay? So we say a decrease, or rather we can say, a decrease in pressure, or we can say an increase in volume, right? So an increase in volume, all right, will favor the side with more moles of gas, more gas volume, all right. So we know the reactants have a greater volume, right? The reactants have a greater volume of gas, therefore the reactant side, or we can say the reverse reaction, is favored, okay, and therefore it means that that will decrease the yield, that will decrease the yield. Okay, right, so you can write this in your own way, but of course I've tried to explain that, every time that we increase pressure, we favor the side with less moles, but when we decrease pressure, in this case, we favor the side with more moles. Okay, right, hopefully. And if you don't understand this, ladies and gents, it means you haven't watched my longer videos on this section. Please, you'd be doing yourself a huge disservice if you don't do that. Okay, I promise you, after watching that, you will thank me for days. Okay, right, now let's go to the next question. They say, now we've got 5 moles of N2 and 5 moles of H2 are now sealed in a 5 cubic decimeter container. All right, if you're going to play the lotto this weekend, please play 5, because we've got a lot of 5s there. They say equilibrium is reached at 450. Okay, upon analysis, the equilibrium mixture, rather, it is found that the mass of NH3 is 20.4, and we now need to calculate the equilibrium constant. Right, so let's, as per usual, okay, we're going to have our table there. All right, so please, I hope you don't mind. I'm not going to draw the neatest table. So we know that's initials, that's in moles. That's going to be change. That's change in moles. That's going to be equilibrium. Okay, that's also in moles. And equilibrium concentration, that's in moles per cubic decimeter. Right, so now we've got nitrogen. We've got 3H2 we've got 2NH3. Okay, right. So in this case, they told us we've got 5 moles of nitrogen, 5 moles of hydrogen that we started with. But remember, they said nothing about the products at the beginning. So we're going to assume that we started with 0, right? And then they tell us that we've got NH3 is 20.4 grams, right? So we need to calculate now the number of moles. So number of moles is going to be mass divided by the molar mass. So that's 20.4 divided by the molar mass. In this case, that would be, remember, you've got NH3, right? So nitrogen in the periodic table is 14, has got a molar mass of 14, and hydrogen has got 1. But how many hydrogens do we have? We've got 3, right? So this is the molar mass of NH3. And please, you do not multiply by the coefficients, right? You only multiply by the subscripts, the numbers at the bottom, right? So nitrogen is 14 plus 3 times 1. That's 3 hydrogens, right? So it means we just simply have 20.4, okay, divided by, so that's 14 plus 3 times 1, which is 3. Okay, so that will give us 1.2. Okay, so it means that the number of moles of ammonia at equilibrium will be 1.2. So we know we've got 1.2 at the end. Now, what I usually like doing, ladies and gents, is that obviously I normally write the change with a different color. So in this case, we started with nothing. So you go to your table and look where you've got the most information. So it's ammonia. So you started with nothing, and at the end, you've got 1.2. So how much did you form or did you make in this case? So it means that you formed 1.2 moles. Now, ladies and gents, the next portion, this is where I want you to please pay attention. Okay, so what you do is you're going to use those change in moles. In this case, you use your ratios, okay, to get the others. So for every 1 mole of ammonia, I get 2 moles of 1 mole of nitrogen, rather. I get 2 moles of nitrogen, or of ammonia. So for every 1 mole of nitrogen, I get 2 moles of ammonia. Now, why am I using nitrogen and ammonia? Because I want the moles of nitrogen and I already have the moles of ammonia, right? So I start with my ratio. For everyone there's 2. So for how much, which is the one that I want over here, right? So for how much will I have 1.2? So for how much will I have 1.2? Okay, and please be careful. The same things must be on the same side. So nitrogen to nitrogen, ammonia to ammonia, right? So in this case, you can just cross multiply. So that's 2 multiplied by x, that's going to be 2x. 1 multiplied by 1.2, that will give me 1.2. You only multiply the coefficients. Please don't worry yourself about all the other things. Now I'm going to divide by 2 to get the value of x. So that will be 0.6. So it means the amount of nitrogen that was used in that case was 0.6. And then let's go to finding the moles of hydrogen. So it says for every 3 moles of hydrogen, I've got 2 moles of ammonia. So for how many moles of hydrogen will I have 1.2? I hope you get the gist of it, right? 2 times x, that's 2x. And 3 times 1.2, that will be 3.6. Okay. And of course, I'm going to divide by 2. And I get 1.8. Someone was laughing at me, actually saying the kind of English that I use. I hope you guys don't really make a mock of me when I use such words as gist. All right. If anything, I hope you're learning something. Okay. Right. So let's get right into it. So then nitrogen, remember, that's our reactant, right? So it means I started with 5 moles and I use, remember you use reactants, right, to form products, right? So I use 0.6. What do I have at equilibrium? In that case, I would have the amount of nitrogen in that case would be 4.4. Okay, I started with 5, I use 0.6, at the end I've got 4.4. And then for hydrogen, I started with 5, I use 1.8. Okay, so at the end I would have 3.2. All right, now let's get to the last portion. All right, so now we want the equilibrium concentration. So we know that concentration is number of moles over volume. So it means you'd say 4.4 divided by the volume, in that case was given as 5 cubic decimeters. So we're going to divide that by 5. Okay, so and by the way, concentration only is for gases, right? And obviously aqueous solutions, right? If it's a liquid or a solid, you can't calculate the concentration of it. Okay, so I've got 0.88 here. We'll do the same for hydrogen. So for hydrogen, we've got 3.2 divided by 5, and I've got 0.64. And finally, I've got ammonia, which is 1.2 divided by 5. And in this case, I have got 0.24. Yeah, man. Okay, so that's 0.24. So that would be 0.24 over there, right? Okay, so now let's calculate our equilibrium constant. Okay, so remember we say that's the molar concentration of your products. What are your products? It's going to be NH3, but remember the coefficient becomes your power. So in this case, that's squared. Please, you don't need to write products over reactants. You just need the equilibrium expression, right? Divided by our reactants. Remember, both my products and reactants, all of them are gases, right? I'm trying to show you that there, right? All of them are gases, so I'm going to include it into my formula. So this is going to be nitrogen to the power 1 and hydrogen to the power 3. Now, of course, we're going to substitute our values, right? So that will be 0.24. So that's 0.24 squared divided by, for nitrogen, we have 0.88. And for hydrogen, we had 0.64. But remember, that is cubed. Okay, so let's calculate there. So 0.24 squared divided by, I'm going to put that in brackets, 0.88 times 0.64 cubed, right? So there we go. So I'm going to close those brackets. Okay, so I get a value of 0.25. That's my equilibrium constant. Okay, so my Kc value is 0.25. And that, ladies and gents, is how that cookie crumbles. All right, and of course, we're looking at the last question. They say the temperature is now increased to 700 degrees, right? They say what will happen to the value of Kc at this temperature once the new equilibrium was reached. Write down only, remain the same, increase or decrease. Now, ladies and gents, what we need to do now is look at that scenario and see what actually happened, right? So remember, that is an exothermic reaction. Sorry about that. So that's an exothermic reaction, right? So an exothermic reaction tells us that we've got heat on the right hand side. Okay, So once we increase temperature, remember, an increase in temperature always favors the endothermic reaction. All right. So if the forward reaction is exothermic, then it means that the reverse reaction is endothermic. So remember, an increase in temperature will always favor the endothermic reaction. So it means in this case that the reverse reaction will be favored. And so it means that your NH3 will decrease. I hope that makes sense, right? So once we decrease NH3, in this case, it means that our Kc value. So you look at this. Remember, Kc expression had NH3 at the top. Once you decrease the amount of NH3, of course, it means that your Kc value would also decrease. So to answer that question, they asked us, will it remain the same or will it increase or decrease? And of course, to answer that question, we say it will definitely decrease. Okay, so our Kc value would decrease. All right. And essentially that is the end of our question. All right, so that's 6.5, and we know that that will decrease. All right, ladies and gents, I hope that you enjoyed this. And of course, I will be coming back again during the course of this weekend to just give you some more nuggets here and there on chemistry. Otherwise, from me for now, I'll see you guys next time. Sharp, sharp.